So I think we'll wait for another minute and then start. But well, most of us are here already. So uh, if anybody is interested in playing along with the code while I do the explanations of how you typically go about using the C-cube library for optimal control, I have posted two links in the chat. One of them should, I think three links. One of them should take you to the code repository on GitHub. The second one, which says something like binder, something, mybinder.org, that should take you to a live notebook where you can play along and not have to install anything. You just click on that link and then you click on examples and you see a bunch of Python notebooks. I'll go through that later, but in case anybody wants to already take a look at things, that's a good way. Because it does not involve any installations. You just do everything in the browser. And then I think there's a link for the documentation. Yeah, I think we're past 5 minutes, so I'll just start.
Just before you start, very quickly, is it okay if the people from WMI that are using the code with me also join?
Yeah, the more the merrier.
Okay.
All right, great. So this is a more software and user guide centric talk on C-cube. We have had a bunch of more research and algorithmic overview of the whole project and the library previously. And we have Nicholas and Federico. So if any of you have questions regarding those things, I'll just direct you to those people. But okay. So yeah, so C3, we have already published the paper. It came out earlier this year. So please applied, and you can see it here, but we'll be focusing more on the second line of the code that lies on GitHub and how that is structured and how basically how do you write something in C-cube to perform optimal control. All right. This is what we'll be discussing. First, we'll do like a 1 minute crash course in the 1 hour talks that Nicholas and Federico usually give on the C-cube, research part. And then we'll dive into each submodule and what is involved in working with those submodules. So this will be probably relevant to somebody who wants to, contribute more to the C-cube code base, or somebody who just wants to be an user of the library for various control tasks. Okay, so yeah, this is a very common diagram that we use to convey the idea behind the C-cube library, that you start off with an initial model, and given that model, you find the best pulses, and this is purely model-based control. And once you have those pulses, you construct an evaluation sequence, and then you do calibration on real hardware. So this is like proper closed loop hardware-based calibration work that you do in the C2 step after the model-based control in C1 step. And once you have done this C2 step, that's typically where most workflows end. That you had a model and then you did some calibration on your hardware, and great. So now you have a bunch of optimized gates. But we take it one step beyond that, and the data that you collect in this C2 step is in fact very useful for updating the model that you had originally. So you started off with a model in step 1, and the data that you collect in this step can actually help you update the parameters of that model, so that when you start again the next time, you don't start from scratch. You have a model that is now slightly better than the previous model and slightly closer to being a really good model. So that's what the C3 step essentially entails, that you do model learning. And it's essentially a step for machine learning on the data that you collected in the C2 step for a better version of the model that you had in the C1 step. Okay, so now that we know what are the three control, calibration and characterization steps in the C-cube library, we'll go through each one individually. So again, so if you see below, we note that there is an example. So I'll run through the presentation over the next 10, 15 minutes, maybe 10 minutes, and then we'll look at actual notebooks where you'll see the code and how this thing actually gets written down in the form of a program. So yeah, so for the first step, what you have to do First is that you need to define your qubit or your device. Well, the most common qubit device that we use in the C-cube package is a superconducting transmon, but the idea is that this expands beyond just transmon-like devices. And once you have defined this qubit, and when I say define, this typically means that you are defining the Hamiltonian of that physical device, of that qubit. And once you define that physical Hamiltonian of that qubit, you want to also define or also set up the control signal chain. So this is in line with what you would have in your experiment in the laboratory, that you would have a local oscillator, you would have an AWG. So you want to set up all this control stack that exists in the laboratory as well, which go down to your qubit and provide the different drive pulses. And once you have these two things, the qubit and the control stack, you want to define the gate set. So basically the instructions that you perform on these qubits with the electromagnetic pulses that you send through the control stack. And once these three things have been defined, that's when you have, let's say, a minimum quantum computing device. So then you want to do optimal control. And at this point, the optimal control that you do is purely based on the model that you had. So there's no hardware that we're interfacing with yet. And that's why it's gradient based, because you can take gradients of your models. And a very technical part of this is that we use this library called TensorFlow, whose main selling point is that it lets you take automatic differentiation for very, very complicated programming models as well. So that helps a lot. And besides the obvious benefits of being able to differentiate over very complicated program chains, these also run transparently on GPUs. So if you want to accelerate your code by running them on various accelerated hardware, that becomes straightforward because of the choice of library that we have used here. Okay, so we'll come back later to this and we'll look at an example that shows step by step how this model-based optimal control is performed. But now we go on to the next step, which is C2, which is black box calibration on real hardware. And here you start off with defining an evaluation sequence. This could be something like orbit, and then you need a goal function, basically something that you will be optimizing for, and you need to interface with the control hardware. So here is where we start talking to real hardware. For example, you might have a Zurich Instruments control stack in your laboratory, which has all the AWGs, the measurement tools, and the UHF QA, and all their different quantum analyzer stack. And you want to interface with that because your C-cube software will directly talk with that hardware control chain for the black box calibration. And you also deal with the readout. Sorry. So you deal with the measurement results, and these results could be at different forms. They could be like right now we deal with the average shot data, but it could start very well from raw IQ data or something after the discriminator at different stages. And this is also where we store these experiment results. So every time you send an instruction to the qubits and you get back some readout, you want to store that, because this is what we'll use in the next step for the model learning phase. So that's also done by the library in this part of the code. And once you have all this set up, you want to again run an optimization. So all the three steps in the C-cube library at the core are optimization steps. You are either optimizing a model, you're either optimizing on hardware, or you are optimizing for the data that you have to update your model. And in the optimization of this C2 step, we perform gradient-free optimization. So while in the C1 step, we were doing gradient-based, so we would use something like LBFGS. In the C2 step, which is gradient-free, we typically use something like CMAES. So that's kind of how far we have reached right now, that we have interfaced with hardware in the laboratory, and we have done calibration on that hardware with gradient-free optimization. I'll also show an example notebook that shows how this gets done, and we'll come back to that. But now we'll move on to the next step, which is the model learning. So this is, let's say, the youngest member of the C-cube library, because a lot of this work involves interfacing with experiment data from hardware. So we talk to our partners, we get data from them, and then we have some initial model that is based on whatever the prefabrication model that they had, and then we update that model based on the data that they collected during the C2 stage. And what the data, like in a very crude form, looks like is that you would have pairs of these pulse schedules and the corresponding readout data. So, okay, this went in and this came out, and this is what I had in the hardware. I want to replace it with a model in between, which as close as possible emulates that hardware. So in typical machine learning language, you would define a loss function, and then you'd iterate to minimize the loss function based on that data set that you have. So yeah, so I'll not be showing an example notebook for this, but we can discuss it more once I come back later after showing the example notebooks. Yep. So we have a big group working on a lot of new features for the C-cube library, and I'll be quickly going over some of the things that we have work in progress right now. So for example, I am working on the experiment control stack integration, and this involves working with our partners at, for example, Quantify or Zurich Instruments to essentially interface the C-cube library, and more specifically the C2 step with the real hardware stack. And along with that, I don't know if we have any experimentalists in the audience today, but oftentimes collecting that data and storing it in a database form so that you can read, write off it later on, and I don't know, share with your collaborators or use it for a publication later, that becomes a challenge. And you have all these directories full of data here and there lying around. So we are also working on having an integrated database inside the C-cube library or as part of the different plugins, so that data that you collect, which is useful for us as well in the model learning stage, is easily portable. Another very exciting work for us is the pulse representations. So we started off with somewhat of our own definition of pulses, in how how you define the waveforms, how you define the pulse, the different parameters of the pulse inside the C-cube library. And we gradually started adopting the Qiskit pulse style representation. But as we work with more and more partners, we see that the Qiskit pulse style is designed to work with IBM's hardware. So of course it has certain quirks and let's say funny features that are optimized for IBM's hardware. So so we're looking at other pulse libraries as well, like the one from QTech, the QPulse, and similar ones to essentially expand our current pulse representation to be more flexible for different pulse representations that different hardware partners use. Because essentially we don't have a choice, and it all depends on the hardware stack that we integrate with, that how do they define their pulses. So we want to have a representation that's as flexible and as all-encompassing as possible. Then we have Kevin and Miralem, who are working on a very comprehensive and elaborate library of optimization algorithms. I think Miralem already previously presented his work at the Control Club a couple of months back, and that work is maturing a lot right now, going towards the direction of getting a public release soon. And that will then form the backbone of the optimization algorithms in the C-cube library, essentially making sure that we have control till the very lowest level for all these algorithms like CMAES, LBFGS, gradient descent that we use in the code base. Then I think many of the experimentalists will also appreciate the need for a GUI for setting up and tracking the simulation runs. And once I show you the notebooks, you'll probably feel the need for it even more. But yeah, that's also on the cards, and we have more experienced developers on the team now who can help us in that direction. Nicholas and I are working on something called experiment design. Maybe we'll not discuss it today, but the idea has come up previously as well in several Control Club talks, where you essentially have to are given with the task of finding the best possible steps that you can define if you want to identify a particular parameter of interest. to a certain degree of precision. And yeah, we are working with Matthias and other people to essentially also have integration with hardware, so we can talk to the experimentalists in the whole process of iterating this experiment design module. Then let me see. Do I remember who's working on? Yeah, Urek is working on modeling physical devices beyond transmons. So, like I said in the first slide, we have transmons as the most common device structure right now, but the idea is that we expand beyond that. So, Urek is essentially is looking at a lot of different device models. And then who's working on spam? And okay, so that's Thorge. Thorge is working on a more sophisticated readout library for us, and that also takes care of spam and similar aspects of the readout process. And then the last but not least is the work on propagators and different types of propagation, and we have Francesco working on that. But yeah, that kind of sums up most of our ongoing development directions. Great. What do we have next? Yeah, so this probably won't be interesting to everybody, but might be interesting to maybe Romanas and maybe also the other people who are interested in the code structure of the C3 library. I'll go through this quickly so that I don't bore the other ones who are not interested in this. But what you see on the extreme left are the very fundamental building blocks of this library. We have the system, the signal, and the generator. But the more understandable names for them are the system is essentially what I described as model in the first step, a device model. And then the signal are the instructions. So gates and pulses that you perform on the qubits. And the generator is the control signal chain, so the AWG and similar parts of the whole stack. So once you have these three building blocks, you bring them together under an experiment object, which I think is quite mnemonic because that's what an experiment involves. You have a qubit, you have a control stack, and you have some instructions that you perform on these qubits. So that experiment encompasses or like subsumes these three building blocks and creates an experiment object. And once you have an experiment object, then you can do several things with it. You can simulate running instructions on your qubit, or uh, you can read write from different configuration files for your device. But what's probably most interesting is that you want to do the optimal control tasks that I previously described. So you want to do C1, C2, C3. So that's where our optimizers come in. And I think now it makes sense in the light of what I was telling previously, that whatever the C-cube library does, at the heart of it, it's all optimization tasks. So you have this C1, C2, C3 optimizers, and you have this experiment object. What you need two more things, maybe three more things. You need a goal function, something that you want to optimize for, and you also need a parameter map. What's a parameter map? A parameter map is nothing but it extracts the various different properties and parameters of the experiment object into a vector of parameters that the optimizer can optimize, right? Like you have a goal function and it's defined by a vector of parameters and you want to optimize them. And at this point, you have everything that you need to optimize, except like how do you optimize? So that's where the algorithms come in. So in the library, you have this whole, in the C-cubed software repository, you have this whole structure of libraries, which are mostly code blocks or features that are used in different parts of the code. For example, the algorithms would mean the algorithms like LBFGS, CMAES, gradient descent that get used in different parts of the optimization stack. So now you have everything in place and you can run your either model-based control or hardware calibration or model learning. So I hope that gives a quick overview of how the code looks like inside the repository. Along with this, we have certain knickknacks here and there. So you have an util section, which consists of a lot of convenience function. We'll look at a few of them later. For example, if you want to define randomized benchmarking, you don't want to like write your own small code for randomly pulling in gates, right? So there's a convenience function for defining randomized benchmarking on orbit of any length that you want to do. Similarly, we have these plugins. That's what you see on the right. These plugins exist independently of the the C3 code base, and they help you interface with outside tools. For example, the C cube Qiskit library lets you define your structures in Qiskit and then simulate them with the simulator, the physics-based simulator that we have. Or the C cube QCCS lets you integrate with the Zurich Instruments hardware. So these plugins exist independently, and based on what you want to do with the C cube library, you would install one of these plugins. Great. So we have covered the code structure, and now we look at the live demo. So I already posted these links previously that we'll be looking at the notebooks with binder. Maybe I'll quickly show you again. So that's the third box that you see here, online live demonstration. If anybody wants to run the notebooks along with me, they can do that. Let's see if I can go to that notebook. Yep. Yeah, so this is what the binder window looks like once you launch so once you launch the window, it'll open a tab like this where it says that it's launching the server. Once the server gets launched, we will have the notebooks. But the two notebooks that we will be looking at today are the C1 step and the C2 step. So first off, we'll be looking at the C1 step. I'll be going through a notebook that's already previously run. You can also take a look at this notebook. This already exists in the GitHub repository. But if you're interested in actually playing with code, then I recommend that you click on the binder link and then click on examples. And then the first one that we're looking at is the 2 qubits .ipython notebook. But yeah, let's go back. Let's see what we have. Okay, so starting off, just to set, so now we are looking at the C1 stage. Maybe if I can go back to my notebook. Yep. So the C1 stage. So we have to do these four things. We have to define a qubit, we have to define a control signal chain, a gate set and instruction, and then we optimize it. Let's see how we do that. So we have a bunch of imports from the library. Nothing interesting going on here yet, but okay. So this is the qubit model that we are going to be simulating today. Like I mentioned, the default multi-level qubit is a transmon modeled as a Duffing oscillator, and we define the frequency and the enharmonicity. And so you see, it's a lot of code that you would write to define your qubit, right? For example, you have to define the qubit levels, the frequency of the qubit, then harmonicity. You can define the T1, the T2 star, the qubit temperature, and then all of these come together in the form of a chip.qubit. So I mentioned this previously that just when I was talking about the C3 code structure, that you would have a qubit, and then the qubit itself will have different properties. Now it might look like that this is a lot of code, and do I have to write it every time? Not so. It's a lot of code because we want to demonstrate how it is done, but actually in production settings, or actually when you're running this in your lab, you would have a config file, and I'll show the config files later about how they're structured, but you can read all of these from that config file. So you don't have to write this every time you run a notebook. You just write it once, the first time you set up C-Cube to work with your hardware. And once you have written up the config file, you just read off the config file every time, and you can share a config file freely. It's just an JSON. It's just a JSON file, so it's very portable. There's no lock-in to the C-Cube, the style of representation, or no lock-in to the local hardware, your computer platform. Nothing. It's very portable. But yeah, you define a qubit like this with the properties that I mentioned previously. So you have these 5 properties or the 6 properties, and then you put them inside a qubit structure. And then you do the same for the second qubit that we have. And once you have 2 qubits, you want to define a coupling. So this is the part where you define the coupling along with the coupling strength. And that's basically all that you need for defining the coupling strength. Okay, so we are done with the first step of defining the qubit model. The next step that we had was for going ahead and so we'll now move forward towards the next step of defining the control chain. And as you can see, we define a drive line. two drive lines well for the qubit, and you'll see later on how we elaborate on these control chains. But as a quick detour, because so like I mentioned, we have Thorge who's working on a more sophisticated readout and spam library, but this is what we have right now. You can define a confusion matrix, and with that confusion matrix in place, you can simulate spam in the readout. All right. So there are also some utility functions mimicking what you typically have to do in your qubit. So one such example is that you want to create an initial thermal state for your qubit, and this is what is a task that you initialize your qubit. So it's a task that is performed on the qubit, that you initialize it to a ground temperature, to a ground state. But okay, so now that all of these things have been defined, you collect them in a model. So that completes the first part of our model definition. And the drives that we defined previously, now we'll go ahead and define the control signals that essentially go up to those drives. Okay, so coming down to the control signals, you see we have this very mnemonic objects of the device class, or like subclasses under the device class, that you have this LO, you have an AWG, and you have a mixer. Again, trying to mimic or trying to emulate, or an even more probably complete term is a digital twin of what you have in the laboratory for your hardware stack. So once you define these things, you can again set their properties similarly the way we did previously for the qubit. And you can also mimic how there is typically a finite resolution that your device will be having, because so there's a rise time that you typically have when you have a pulse in the laboratory. It doesn't go up instantly, and that means there is a certain slope, and that's what we show here, that waveform generators have a rise time, and you can also model that in the code, that it's not an instantaneous spike. Okay, instantaneous step. All right, so now that we have the control electronics in place, the next thing that you want to do is more detailed definition of the generator, because so we had this smaller building blocks of the AWG, the LO, the mixer, and now we put them all together. So that's what you see here, that we have a generator object which puts all these smaller building blocks together, along with the mixer, the response function, and similar tools coming together. Okay, so I think that completes our step 2 or step 3. Let's see. So we have completed define device, we have completed define control signal chain. Now we are off to the third step. So gate set and parameter map. So for this step, it's the typical approach you take for a gate-based quantum computing chip. You define a gate set, and the gate set involves defining a gate time as well as the envelope of the Gaussian and a bunch of parameters that parameterize that whole pulse. So yeah, so this is again very similar. So you might be seeing that the code looks similar in each stage, and that is how it is supposed to be, that at every stage you have all these quantities, which is like a value with a minimum value and a maximum value and some units, and all of these quantities define certain properties of the building blocks, and then you bring together all these building blocks into one conceptual block or box, however you put it, which then interacts with the other people, with the other blocks. All right, let's go forward. So you typically also want to define a pulse that does no driving, and this comes handy during the simulation steps. More pulse definitions, but yeah, those were all the pulses that we defined. Now you want to collect them together in the form of instructions, and by instructions I mean like a typical RX90 gate or like an RY90 gate, the common terminology for your gates in a gate-based quantum computing chip. Great. I just hope that you don't get like intimidated by the wall of text. It's not like you have to do this every time, and I want to harp on that because oftentimes you open a C-cube notebook and it looks like there's just so much code and so much boilerplate I have to define. But that's there for the sake of understanding, and you would not usually be writing all those things down. And now or later might be a good time when I show you the config files. But okay, we have all the three parts that we needed. And I mentioned this previously that once we have all the three parts, we will be putting them together into an experiment. So that's what we do here. And I also mentioned about the parameter map, which brings together the parameters based on which we'll be doing the optimization tasks. So you see that here that we have this PMAP object and we have instructions, we have the model, we have the generator, the three things that I mentioned previously, which form the building blocks. Wonderful. So now we have all the building blocks and you can play with them. We'll be simulating them. So that's the playing that we're doing today. You set the optimize the OPT gates. What does this mean? This means that let's say you have defined that your system can perform three different types of gates, but you only want to optimize one certain gate. So that's what we do here. But you can also optimize all of the gates. There's nothing stopping you from doing that. But the interesting part is that once you optimize the gates once, or once you compute the propagators, propagators in this case means that once you compute how over every dt time step the device is progressing, that's it. Once you have done that computation heavy step, you don't do it again and again. And I think that helps us a lot in reusing pre-computed values. So once we have computed the propagators, the unitaries for a certain gate set, we don't have to do it again and again. So if you run it the next time, you just use those pre-computed values. And it's important to understand this. This is not just unitaries or not just a perfect gate representation, but you are actually modeling the physics underlying it. So you are calculating the time evolution over every dt time step. And this is what I was mentioning, that once you have created the unitaries from this time evolution, you can store them and you use them as many times as you need to. At that point, it's just matrix multiplication, no longer computing of propagators. Okay, so this is where those, once you have the gate set, now you want to perform the operations. And like I mentioned previously, that let's say you have an initial state which looks like this, all zeros. And then you want to perform one operation on it. So that's where you would be doing the dynamics. But yeah, so this is just some helping code for making a pretty plot. But this is what it looks like. Not too great, right? Which is expected, that there would be quite some leakage and the populations would not be completely going to the 0 or 1 state as we expect them. But we'll see how optimal control helps to improve this. So this is, of course, a very unoptimized gate. And if we do it for 10 times, like I mentioned previously, this step is very lightweight. You don't have to compute 10 evolutions again. You just have the unitary stored previously and you just multiply them. And like we saw before, it's still a very bad gate. Great. So now we have a chance to improve this gate, and we'll be doing it through open loop control. So one option that we set here is that we enable the drag pulse, and that's as straightforward as just enable drag to, and it will enable the drag on that particular device. But now we have a bunch of gates that we want to optimize, and we also have certain parameters of that gate that we want to optimize. So for example, these are the parameters in this case which we'll be looking at, and a more prettier looking format is out here that we are trying to optimize this RX90P gate, and these are the parameters that we'll be optimizing. So now we come to the find optimal pulses step of this C1 example, and we have already gone through the left block, the three parts of the left block. We have gone through C3 experiment, and we have also gone through C3 parameter map. So now we'll be looking at C3 optimizers. So that's what we do. We import the C1 optimizer and again some basic boilerplate code for setting things up. But we'll be having 30 evaluations of the function for this case. and we'll see how that optimizes our gate. So now we have a much better population that we see here, and there's a lot less leakage, and the gates look a lot better over like 5 sequences. So yeah, so like doing the actual optimization is very little code. So I think this is the bottom line, that all the setup that you did previously is something that you'll be reusing again and again. And it's very possible that you actually start writing your notebook from this step, and it's just 1, 2, 3, 4, 5 steps for doing the optimization. And maybe now we take a look at what those config files look like. They look very much like the code that you saw, just they have been put together in the form of JSON dictionaries. So for example, this is the config file for the generator, one such generator that we use for testing our code. But like you see, it's very human readable, and this is all similar to what it looked like in the code base. And you would just have this file in your local directory, and you just read off it, and you reuse it as much as you need. And if you need to, for example, add another qubit, you have already a config file for a previous similar qubit. Well, that's it. You don't need anything else. So yeah, similarly, like a lot of things are defined in this config files, even how your whole experiment is structured. So even not just the device models and such things, but the actual operation also is something that gets defined in these configuration JSON files. And it can read off the device model, it can read the generator, and then you can already instruct. So yeah, the conclusion that I would like to convey is that things can be reused very easily, and you can script things. I think this is also relevant to experimentalists in the audience who want to have this form of scriptable pipelines. If we are looking at more automation of the device characterization and calibration workflow, you want it to be fully scriptable. That you have one script and you call something as simple as ccube.sh, and that just runs the whole thing. It starts with a model, does the optimal control model based, then takes that and feeds that to your C2 step. So that is very much possible already in the current stage, that we have the ccube library, that you can you get a new qubit setup on a Friday, and you start the script and you come back on Monday and your device is optimized. That's possible. Okay, so now that we have shown model-based optimal control, let's go and take a look at the calibration work on the hardware. So if we go back to our presentation, this is what we need to do. We need to define an evaluation sequence, we'll define a goal function, then we'll interface with the hardware, we'll deal with the readout, and then we'll optimize. And this time we'll be doing gradient-free optimization. Nice. So for the purpose of this experiment, for the purpose of this demonstration, we are not interfacing with any real hardware, but we're interfacing with a black box. And the idea is that this black box can only take in whatever my real hardware can take in. So for example, while I'm working with our partners at Zurich Instruments, our understanding is that there is the Zurich Instruments black box. I don't know what lives inside it. All I know is that it can take 5 parameters: the pulse amplitude, the pulse frequency, and maybe 3 other things, the pulse duration, things like that. So that's a similar approach that we'll take here as well. We'll be having a black box experiment, and that black box can only take in these parameters P. That's it. It doesn't take in anything else. So that's just to convince you that we don't actually have access to the hardware. So it's all, calibration that is purely black box. But just going back a few steps. So remember I was mentioning those utility functions that we have, and one such utility function is the randomized benchmarking. So it's nothing. It's not something very fancy, but it's a small thing that's very useful in your day-to-day work, that you have a randomized benchmarking and you want to change the length. You can do that. You can very easily do that. And if there is somebody who's already looking at our examples on the binder notebook, they can see that this is also very easy to change. For example, let's see. Okay, I'm doing this along with you. If things go wrong, they're just going to go wrong. We'll wait for this to run and we'll come back. Yeah, so this is what I was mentioning previously about the black box, and we have an orbit wrapper, but all that means is that I have a function to which I pass p, and that's all I can do with it. Everything that exists inside it is a black box. Um, I think I need to make this clear because it might look like that I'm not really interfacing with any hardware. So am I cheating? Well, no, it's not. It's not like you have access to that hardware. The only access the optimizers will have, as we'll see later, is that it can pass some parameters to it. That's all, nothing else. But this is very similar to the device that we were looking at previously. And okay, this has run. Great. So now, yeah. So we have an RB length of 5 in this case, which is the output you get like this. Let's say we change this to RB length 10. Yep. So now you get a different randomized benchmarking set of sequences. So yeah, small things that make your life easier. But coming back to our calibration on black box hardware, what do we have here? So I showed you the black box. That's the hardware. That's all we have about it. We forget anything else. All we can do, as I mentioned, is that you have a bunch of parameters. It takes in those parameters, gives you a readout. Nice. But you also want to represent this experiment inside the C-cube structure in the same way that I mentioned previously, that you have these representations of the experiment inside the C-cubed library, so that you can have a digital twin of that hardware. So that's what you are doing out here. You define the gate set, basically the instructions that I mentioned in the very first slide about what all we need. And these are the instructions that will be performing on the hardware for the calibration task. And again, they look very familiar and a lot of text because we have already gone over this in the previous presentation. But yeah, the bottom line is that you take all of these things together and form an experiment object. Now, the next step comes is that defining the parameters, very similar to our previous. So I find this very useful for myself to understand that my workflow is the same no matter which step I am performing. I get a bunch of building blocks, I bring them together, then I define the parameters I want to optimize, and then I run the optimization algorithm. We do the same thing here. We have the optimizer map, and you have a bunch of parameters that you wish to optimize, and you can again see those parameters like I showed in the previous notebook, and then you have an algorithm. In this case, we'll be using the CMAES algorithm, and we're doing 300 function evaluations. So in this case, function evaluations means that we are performing 300 interactions with the hardware in the laboratory. Okay, so much like before, the actual optimization code is very little. You define an optimizer object with a bunch of options, and off you go. You have the parameters, and then it starts optimizing. And this is sort of the view that you get. And we can also run this here, actually. Let's see if I bring this back to 5. And while this runs, we'll see what's happening here. So at every step, it's performing 10 evaluations. So this is like a typical CMAES style operation where you'd have a certain cloud of points that get evaluated at every step, every iteration of the optimizer. And like we mentioned that we'll have 300. So as soon as it goes to 310, that's it. It doesn't do any further optimization. But now we can look at the analysis, that how does the orbit, because we're doing orbit, right, for the calibration task. So we'll see how the orbit progresses over time. Again, some basic plotting code, but yeah, this is what we have of interest. So the red dots that you see are the orbit number. So basically in orbit, you have this whole bunch of gates that evaluate to an identity. So if your gates are perfect, you should be getting the same state that you started off with in the first step, but depending on how good or how bad your gates are, you will have an error. And the lower the error, the better calibrated your gates are. That's what we see here, that over time, these red dots keep going down further and further, and at the 30th iteration, it is already going down to like 0.1, close to 0.1. The blue dots, the gist of the blue dots is that they are the cloud of points that are getting evaluated. And as you progress in the orbit with our CMAS optimizer, the cloud keeps shrinking. So the uncertainty increases and also the optimization progresses. So that's the idea behind that plot. But yeah, so we have it running, I guess. Yes, we do. So I'm running this live. This is not running on my computer. It's running in the cloud, not my cloud either. And you can also run this notebook now after the talk. Does not matter. The link stays. And the link is also on our repository. So I'll also show how to launch it from the repository later on. But yeah, like you see, for example, in this case, we have already run 50 function evaluations and it's still running. And at every step, you can see the function value keeps going down. But yeah, typical CMAS operations. All right. So those were our two examples. Now that we are done with the examples and the code structure, I think that's all I have on the presentation side because the live demo is done. I do have a quick developer tools and operations section. So I'm partly sure that most of the audience here has already attended a previous talk I gave about how we do development at C-Cube, but I'll just rush through it. And there's a link at the bottom that will take you to my more detailed presentation on how we do development at in our team. But yeah, the bottom line is we have a test suite that is written in PyTest, and we have a documentation that is built with Sphinx in the NumPy doc style. We believe static type annotations are, well, at least I believe type annotations are very, very important. So we use MyPy for our type checking and type annotations, and we enforce code formatting with black and flake 8. Our development takes place on GitHub. So GitHub Actions is also what we use for all our automated releasing, because I showed previously that our code is on pip, right? So that all happens automatically. Like every day there is a new nightly version released. Yeah, maybe I should go back to that slide. Yeah. So there are two versions you can install. You can install the C3 toolset, which is the stable master. And we also have a development version, which is probably more buggy, but more up to date with the features. And all of these releases take place automatically through GitHub on pip. Well, that's all. I'm open to questions. If there are no questions, then that's even greater.
So I have a few questions. Can you hear me?
I can.
Perfect. So thanks a lot for the talk. Sorry. Thanks a lot for the code. So the first question is about the parameter mapping. So what is the sigma that I saw in the notebook? I didn't get actually.
Which notebook do you remember? Which notebook you're referring
For
to?
instance, when you for instance, there also you just.
Okay, where is the sigma? I'm missing.
Sorry, when you define the controls, probably where you have the amplitude, the tuning, the offset.
Nicholas, do you quickly know what he is referring to?
I guess it's the width of the Gaussian.
Okay.
Okay.
Or it's just some pulse parameter.
Okay, so you essentially here you are parameterizing with the drag style. So okay, got it. Okay, so actually sigma. Okay, so you have the control both in the x and y direction, right? And that's why you have the XY angle then. Okay. Yes. So about the model, where you define the Hamiltonian actually in the C1 step.
Yeah, maybe while you scroll to the section. So there is a library of Hamiltonians, for example, in the excitation basis that we used in the write-up. So maybe, Anurag, you can go to the library of Hamiltonians. So we just take it from there. It's very straightforward.
Okay.
So right now, as you said, we have everything written in like an excitation number basis. So what the model will do, it will find the annihilation operator for the whole system, and then this one is used to build whatever, a number operator or a quadratic or an interaction, like a dagger plus a type things. Yeah.
And going forward, I totally see all kinds of wizards and UI to help you put in these initial configurations. So, I mean, right now it works and it works well, but it may be not the most user-friendly it could possibly be. But, you know, once you have a JSON to put a GUI on top of it to fill it in, that's not super hard. So we'll probably do that.
Nice. So I have another question. This is more the benchmarking programming code. So did you benchmark TensorFlow with other libraries so far, or you just let's say choose TensorFlow because it's the common one and also can help you a lot for the model learning part?
I don't think we have benchmarked. We started with TensorFlow, and I think it is there somewhere on my to-do list that I need to make a benchmarking library that essentially benchmarks our code over time and finds out when we go bad. But comparing TensorFlow to, for example, Torch or JAX, no, not done yet.
Okay.
So
actually,
the primary, just the primary motivation for the choice was the automatic differentiation. So that's kind of the critical part, because otherwise both C1, which is the optimal control, and C3, which is the model learning, but also stuff that you haven't seen here, like the co-design or the experiment design that Nicholas is working on, none of these will be gradient-based. So whatever numeric tool we use, it has to support automatic differentiation. Beyond that, honestly, we don't really care.
No, and when we started almost 2 years ago, we just used TensorFlow because it seemed the most usable, or also from an outsider perspective in this. And right now, I think there's a lot more libraries to choose from, so we are open for an reevaluation.
Yeah, I think like when you started, this was like TensorFlow 1.x, and now we have like JAX was not even in the picture at that point. It was a very, very early phases of JAX, and also Torch was very unusable. It was just been released by Facebook like a year or so back. So these libraries have also matured a lot now. For example, Torch did not have a lot of support for complex numbers back then. They do now. So in all probability, there might be better choices, but yeah, not done yet.
Okay. I mean, just to say that in our GitHub repository soon will appear, let's say, some gradient bases that was developed by a guy in Ulm, and he used actually JX to work with the automatic differentiation. So maybe at some point it makes sense to see what is the best one.
Yep.
And yeah, just to mention this. And
Can I?
I mean, yeah, sorry.
Hi, can I have a question?
Yes, please.
So how does the C-cube refine the model after the learning process?
I don't think I understand the question.
So someone has a huge echo. Maybe it's worthwhile trying to mute ourselves when we're not talking.
Yeah. So I didn't follow your question.
Okay, so how does C cube try to refine the model? Because you have this
Oh,
learning process also, right? Because in your example, you have is a model, and then
yes.
you take that models, and then
So the model
for
has
example,
certain parameters, right?
yeah, with a
When we
certain
define the
parameter,
model.
you run it, and then
Yeah.
you try to find the optimization. But then you have the third step is actually a learning process, and then how 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 the model is refined after the learning
Ah,
process.
so you have a model that is parameterized with certain parameters,
Okay.
and once you have data, you essentially want to update these parameters of
Mhm.
the model based on the data. So you want to update the parameters so that they best fit uh, the the output that you have received from the
Yeah.
C2 step from the hardware. So you are essentially updating your model by updating the parameters that define the model.
Ah, okay. Okay. Yeah. And what kind of learning you have? Learning library you have? Let's see. The option to do the for example, if you do this reinforcement learning, so what kind
No, we
of
don't. I don't think we have reinforcement learning yet.
okay.
Yeah.
But you do have like direction to go there, right? So because is it or you think that reinforcement learning is not very relevant to this? Uh, can you give a comment like that?
Shai, do you want to comment on that?
Yeah, it's not a yes or no answer. It's a little bit tricky.
Okay.
Ultimately, you predict the experimental results from the model, and you can measure how many sigma your data is away from the model, and you
Mm-hmm.
want to minimize that. Okay.
Mm-hmm.
For example, C3 can produce sensitivity plots to show you the landscape, so you can know whether you localize your parameter well, and you can see it in the paper. Now, there, I don't see reinforcement learning as being very useful because you can get a feedback immediately. Kind of, you modify model parameters, you resimulate, you get the feedback. Right. So reinforcement learning works well when you don't have you kind of cannot reevaluate the goal function on every step, but only every few steps. So this is like standard stochastic gradient descent and stuff like that. There are issues with respect to which optimizer to use and etc., where reinforcement learning could be very useful. And we're looking at reinforcement learning in that context.
Okay.
So, and in that respect, if you look at calibration, that might actually look like a reinforcement learning task. Right?
Okay. Okay.
Unlike the model learning. So it's kind of very specific depending on which optimization we're doing,
Okay.
whether reinforcement learning is the right tool or not. So it is in some cases, not in some, and we can kind of. It's a very interesting discussion that I'd love to have.
Okay. 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 Thanks very much. It answered my question. Yeah.
Okay. Any more questions? I'll be sending the slides over and uploading them on our common repository of slides. So yeah, feel free to even like reach out to us later as well after the talk. If no
And
more
Tommaso, if you're
questions,
still around, if you could
yeah.
send the recording, that would be great.
For sure, yes.
Thank you very much, Anurag. So I'm sorry I have to leave because also there's another meeting.
Mhm.
So and
Yeah,
then
sure.
it's a
I
great.
think we are wrapping up anyway. So Thomaso needs to pause, like end the recording, and I think we're done. Yeah.
Yes. So let me stop.